Everyone can see the slides.
Yeah.
Okay, so in today's lecture, we will continue with the search algorithms. And last week, we briefly explained the search approach, and then you moved to one of the search method. But today, we'll be reinforcing it. So if you remember last week that we came up with a revised approach that we will start with a frontier, add a node to the frontier, and then we will see if it satisfies the goal test. If not, then we're going to remove that node from the frontier, add that node to the explore set, and then we will move forward and keep on taking the next node. So if you remember this was the example for the revised approach. So if we quickly go through it again, so you will start with the frontier by taking node A, and since node A is not the goal node, so we have tested it and then we put it into the explore set. Then we expanded the node, added node B to the frontier, and again this is not the goal node, so it was removed, and but at the same time it was added to the explore set. Then moving further, we have C and D nodes that come further up. So again, you can see that uh, now we're going to explore one out of it. So let's move towards D. We can also move towards C and E. We will discuss these when we moving towards breadth first search and the depth first search. So again, you can see that in here we see that D is not the goal node, so we will remove it from the frontier and we will add the next node, which is node F. And again, node F is not the goal node, so we will move toward C. C is not goal node. Finally, we move toward E. So the main concept here was that we're going to take a node, but if it is not the goal node, we will put it in the explore set. How we're going to move either towards left or either towards right, we're going to do it in a while. This type of search that we discussed, just moving from one node to another node without any additional information. We don't know that how much is the cost from node number C to E, how much would be the cost from node number B to C. This kind of search is called uninformed search or blind search, where we just move from one node to another node in the search of goal, but there is no information. There is no, I would say, logical information that we can use to reach to the goal quickly, or any logic. We don't have any logic. So this kind of search is called uninformed search. So this approach that we have discussed so far falls to the uninformed search category. Then we move toward the depth first search, and we explained that in the case of depth first search, we if for example you take the same example that we have done in the previous step, we move towards the depth of. I mean, if you're searching any problem, you will move towards the depth of that problem first, and then you move towards the next step. So for depth first search, uh, we will use the queuing problem as last in first out. So the main concept here is to start from a certain point, go towards one direction in a single go, and then explore the other directions. So it's mean that if we have multiple directions, if we have multiple paths, we will go to the depth of first path, then we will move to the next path, and then we will move to the next path. So it's mean that in this case, we are only following one direction at a time and going to as deep as possible, and then go towards the other direction. What does last and first out mean? We will see it in this example. This is the same example which you have seen previously last week. When I was explaining this example, there was a slight mistake that um, while I was explaining correct, but the slides which were running was not for depth first search. It was my mistake, but that's why I'm going through it again. So let's start with the depth first search. Depth first search means we're going to go to the depth of in one direction. Either it can be this direction or it can be this direction. So the main concept is to go to the depth. Or you know that there was another thing that we could have done. What was that? We could have moved here, then C to D, then D to E. This could be another possibility, right? But in case of depth first search, we will not be moving in any other direction until we have explored one direction fully. So this is called depth first search. So now the thing is that whether we move towards left hand side or right hand side, there is no restriction on it. We can move it on either side, but as a rule or as an assumption, whenever we're going to do depth first search or even for your exam, we're going to move first towards the left hand side, just for the sake of assumption. But this is not necessary. You can take the right hand side or you can take the left hand side. But for the sake of assumption, or if, for example, in the exam you are given depth first search, and if it is not stated which side you have to take, you will assume that by definition or by rule, we will take it from the left hand side. Now, as I said that in case of depth first search, uh, we will follow rule first in, first out. What does it mean? It means we will see it in a while. So the very first thing, again, the same concept that we're going to take start from the node. Sometimes you are given, here we are starting from point A, but normally you will be given an initial state. For example, if someone say you to start from C, then you have to start from C. But here we are starting from point A. Let's start from point A. We take in this point, we added it to frontier. This was not a goal node, so we moved it to the explore set. Then we move towards B, and again, B is not goal node, so we explore set. Now the next thing is that you can see that from B we have two directions. We have direction number C and we have direction number D. As I said that we can either move towards D or we can either move towards C. But which one we need to follow at the moment? At the moment, we said that we will move from left towards right. So when we're going to add it in the frontier, we add it in this way. We will add it in this direction, C towards D. And as we said that first in, first out. So it's mean that the very first thing will be checked first, and then if it is not the goal node, it will be taken out and moved to the explore set. So in this case, you can see that node C is not the goal node, but this is the first bit here. So we will take it out. So you can see that we have removed the node and put it in the explore set. And here I have added a node that expand the node, add resulting nodes to the left of frontier. So now in the previous step, you can see that when we move from B to CD, there was nothing in the explore set, so we simply added CD. But now when we removed C and we put it in the explore set, we still have D. So what we're going to do, we're going to add the next node. So you can see that after C, the next node is E. So where are we going to put it? We're going to put it here, or we're going to put it here. So this is, again, as I said, that because this is first in, first out, and we need to go towards the depth, so it makes more sense if I add E here. So let's see. So if I add E towards the left hand side, so it's mean that again, when I will be checking, this will come first. So I can move to the next step and I can explore it. And now I know that E is the goal node. So that's why my aim was to go into into depth of one side. So that's why I keep on adding everything towards the left hand side. Why? Because this is the opening of a queue or a stake. So I need to take the first bit out at each instance. So that's why you can see that I keep on adding nodes towards the left hand side and then taking out those nodes at which are on the first place. So you can see that when I move towards C and D, I taken out C. Then the next node was E, so I kept on adding the next node on towards the left hand side, and then when they are on the left hand side, and as I said that I will take this, I will check it, either put it in the explore set, or if it is solution, I need to return that okay, we reached the solution E. So that's why in this case we saw that we move from A to B, B to C, and then towards E. And if, for example, so here you can see that now we said that the path which was explored was A to B, B to C to E. So if we follow this path, it would be the goal state. And you can see that using this depth first search, we have found this path. So what if we, for example, imagine that E was not the goal node? In this example, yes, so far, yes. But if, for example, E was not the goal node and F was the goal node. So what we're going to do, we're going to keep on moving. How are we going to keep on moving? So, okay, so you can see that we move from A to B, B to C, C to E. We came until this point, right? So after C, which is the next goal, the next goal is D. If, for example, E is not the goal node, the next goal is D, and you can see that D is already in the frontier. So it means that we need to check D first. So if I say that, okay, if I say that E is not the goal node, so it means that I need to put that into the frontier because this is not the goal node. But which one is the next node? The next expanding node should be D. Why? Because we already said that we cannot move towards C because it is already explored. We cannot go towards B, it is explored. So the next possibility would be D. So if you go towards D, you can see that D is not the goal node. So we put it in the explore set. And then finally, which will come after? F will come after. So we just simply put F into the frontier, but now we came to know that that F is the goal node. So now you can see that your path would be A to B, B to C, C to E, and then D to F. So this is your path that your search has found for you, that this is the path you will follow before reaching to your goal state. Okay. Any question on this? Right. Okay. Okay, this is another example that I wanted to explain. Okay, so in a second. Okay, so here is another example. So in this example, you can see that we have a tree structure, and our goal node in this case is M. So you can see that M is here, and we are going to use depth first search to find to reach to the M, and we're going to see that how this search will execute and what path it will explore before reaching to the final goal state. Okay, so as we explained previously that we will start with an initial node. So you can see that if we start here from the initial node, so the initial node is A, but we know that A is not the goal state, so we're going to move further. So if we want to move further, we have B and we have C, right? But we already know that we need to follow, we need to follow from left to right. So we're going to add, so the next possibility is here from A is B, C, right? So it's mean that now A is not the goal node. So the next step is the frontier is empty. So I need to add B and C. Now, Which one so A was not the goal node, right? So A was not the goal node. Next is BC. Now we're going to check B. So here again, B is not the goal node. So now in the frontier, what has been left? So here the frontier was empty, but in this case, in the frontier, we have C already. So now we are at point B, right? So we are at point B. So from point B, what is the next option? So we are at point B. So as I said that we will be going to depth first. So we will not be exploring C at the moment. So from point B, you can see that the next two options are D and E. So what I'm going to do, I'm going to add this D and E to the left of C, right? To the left of C. So now which one comes first to be explored? So this D will come first to be explored. So if we move toward this D, we know that D is again not the goal node. So in the frontier, you can see that you have C and E. But now we need to move towards D. From D, we have two options, H and E. So what we're going to do, we're going to add this H, I towards the left. So now we have this in the frontier, right? So it's mean that the very first thing that we're going to check would be H. So we know that H is not the goal node. So in the frontier, I have IEC. So I will write IEC because there are no further nodes from H, right? So it's mean that depth first search will go to the point to the nodes where there are no further children nodes. I mean, it will reach to that point and then it will move towards the next level. So here you can see that we have IEC. Again, I is not the goal node. So in the frontier, we have C and we have E. So, but now from I, so it's mean that we have also checked I. So from I, who is the next? The next one was immediate to the B. So from the B, we move towards D, but now this path is left. So it's mean that from B, we going towards E. So it's mean that in the frontier, E was already present. We're going to check E. So E is not the goal node. So inside the frontier, we have C here. So we are now at E point. So from E, you can see that we are at E point. So from E, the next two possibilities are J and K. So it's mean that we're going to write. So in the frontier, we have C. So on the left, we will write J and K. Now again, we need to explore if J is the goal node. No, we will write K and C here. Again, there is no children node, so in the frontier would be KC. So again, checking whether K is the goal node or not. No, K is not the goal node. So in the frontier would be C left. So it's mean that now we reach to this point. So again, when we're going to, so now in the frontier, what we have in the frontier, we have C. And when checking C, C is not the goal node, so frontier is empty. So now next to C, okay, now next to C, there are two possibilities, F and G. So it's mean that now in the frontier, I can write F and G. So it's mean that now I need to explore F. F is not the goal node. So in the frontier, I would be left with only G. So it's mean that now I am on the F point. So whichever, you know that whichever node we first move to that node and then check it. So here, if I say that I'm going to check F node and F is not the goal node, I am at F point. It's mean that I expanded to F node and then I'm checking it. So it's mean that at this point, the next two possibilities are L and M, right? So it's mean that now in the frontier, G was already here and I have L and I have M. So it's mean that Now, who will be the next node to be explored? Of course, L would be the next node to be explored. Why? Because it is on the extreme left. So I'm on the L point. And from here, I know that L is not the goal node. So inside the frontier, I would be left with M and G. So it means that I need to move towards the next node, which is M. So it's mean that now after checking, I have in the frontier M and G. So it's mean that now I am on the M point. Well, when I will check if M is the goal node or not, it will say yes, it is the goal node. So finally, I reach towards the final point. So it's mean that before reaching to M, I have traversed so much of path. So it means that this is somehow not a very good approach. Why? Because in some cases, yes, it can be. If, for example, H was the goal node, so it could have found H in a one go. Why? Because in moving in a single direction, it could have said, okay, from A to B, B to D, D to H. So this was a goal node. So it can be lucky in some cases, but if your goal node is toward extreme right, then it could be a problem in finding the goal node. Why? Because then it will keep on traversing the whole path and then finally reach to the end goal, and this is how it will find solution. So it's mean that at the moment what we have done, we move from A to B, B to D. It's mean that indirectly we traverse the whole path before moving to the final location. Okay, so if I circle this, so it's mean that sorry. So if I circle that, it means that this was the whole path which I traversed before reaching to the goal state. So I move from A to B, then B to D, D to H, H to I to E, E to J, J to K, K to C, C to F, F to L, and then finally I reach to the point M. So this is how we move for depth first search. So in this case, you can see that it can be it is not always possible to have the optimal solution, but this is how you find the solution for the depth first search. So if we would like to summarize, you can see that we will start from an initial point, we will move towards extreme left, we will keep on moving towards left, you can see that left, then we will jump from towards the one which was unexplored, and then we will move toward this one, and then finally, so it means that we will start from left and we will keep on moving towards the right. And in this way, we will be expanding to deepest node first and then move towards the right. So this is the main algorithm for depth first search algorithm. Right. So here is an example. So I need help from you guys as well. So if we start from point A, if we start from this point A and we need to go to B, how are we going to do that? One important thing is, I said that in all these examples, we are going towards left and then we go towards right, right? How are we going to choose who's left? Whether the algorithm that we are looking at or what? So always follow your left. So while I'm looking at the screen, so I will be moving in which direction? Towards the left of my hand. So same goes for yours. So you, for whatever example it is, you need to visualize it. You need to move to the left or right based on your left and right. Okay, so in this example, you can see that consider A as a starting point. So of course, the next point, the next node can be this one. I can move to this node, but this is not the goal node. So I move toward this node, not again the goal node, this node. There is no other option. There is no other way, no right or left in this at the moment. So I need to move forward. When I reach this point, I keep on moving further, which is this one. So now here you can see that here you have two options, either to go towards left or either to go towards right. So which direction should I follow? Should I go this way or this way? Which way I should go? If I say this is number 1 and this side is number 2, so should I go to number 1 or number 2? I cannot see if you are pasting it in the chat. You can unmute your mic and you can tell me.
The one.
To the one, right? Because this is towards our left. So that's why what we're going to do, going to move towards the left. Then again, when I reach this point, again, which direction I need to go? I need to go towards the left. Now it's mean that I move toward at this point, then move towards left. When I reach at this point, I move towards left. So it's mean that now left has been explored. It's mean that I need to. It's mean that I need to now go towards the next one. If you remember from this point, if you remember from this, so I need to move towards its neighboring zone. So what is the neighboring side? The neighboring side is this one. So now I need to explore this one. It's mean that this is not the goal node. So now I need to move towards the previous neighboring part. So which was this one. That's mean that now I need to explore this one. Again, this is not the, and you know that you see that when I read this, again, I keep on moving towards left. I keep on moving towards the extreme side, right? Now, these were not the goal node. Why? Because the goal is B point. So I keep on moving. Again, when I reach this point, I keep on moving towards left. And if I keep moving, you can see that then before going to this neighbor, I need to extend this neighbor first, and then I move towards back. If you remember the previous example. So it's mean that I keep on moving, and finally, when I reach to this point, I was told that this is a goal node. So you can see that this was the path which was being searched by the depth first search algorithm. So it's mean that I can move from, so this would be the path that I need to follow. But again, you can see that before coming to conclusion for this part, we did explore all these areas which were redundant paths, which were called redundant paths. Why? Because these paths were not leading us to our solution. These were unnecessary paths. But of course, because of the nature of the algorithm, we did explore these paths, and then finally we came to know that B was our goal node. Okay, so in this example again, so you can see that this is another example for depth first search algorithm. So here we assume that the goal is 3. Why we are assuming? So that we can know that goal can be any part. So you can see that we will start from this initial state 1. Which way I should follow? Which way I should go first? Then after 1, which would be my next node based on depth first search algorithm? You can type in or you can speak, that's fine. Now I can see your chat. So for depth search algorithm, it's mean that I need to, yes, 2 would be my second pass. So this would be my second step. So you can see that the blue one are the one which are being explored. So when I reach to 2, again, this is not the goal node. So which one is the next option? 4 or 5? Which one is the next option? 4 or 5. So I know that from the depth first search algorithm, the further one would be 4 because I come here, then I come here, and then 4 is again not the goal node, so I need to switch to this point. So it's mean that I will come towards 5. Again, 5 is not the goal node, so it's mean that if this is not the goal node, I need to switch toward this point. When I came toward this point, so I came to know that yes, 3 is my goal node. But before reaching to this point, I tend to explore all these paths. Although the goal, the actual path from the initial state to the final stage was from 1 to 3, but because of the nature of the algorithm, we traversed from 1 to 2, 2 to 4, 4 to 5, and then 5 to 3. This was the whole path that we traversed, but the actual path was from 1 to 3. Right. So in this example, you can see that we have, this is our starting point, and this is our ending point. So how are we going to move? Again, as I said, that we need to see should we move towards left or should we move towards right? So in this example, you can see that if I look from my perspective, so this is the left and this is the right. So in case of depth first search, again, as I said, that this is not mandatory. We can start from right and then we can move towards left as well. It totally depends on whichever logic you use, but for the sake of having a mutual agreement, we are saying that we will move from the left. So you can see that I will move in this direction, then I will come here again. At this point, I have two options, either go toward this side or either to go toward this side, but I will not explore this side first. Why? Because I want to use depth first search, so I will keep on moving this path. So again, when I reach this point, I have two options, either to go towards right, which I will not follow at the moment. I will go towards the left, and I keep on moving further. Keep on moving further. I will, so here you can see that again I have a right path and I have a left path, so I will keep on moving left path. Again here right and left. So here you can see that this is the right path, but at the moment I will not follow. I will first go here, but since this is not this is not the goal, so it's mean that ultimately I have to come back here and finally come here. So if you can see that in this case, overall it was relatively easy to reach to the goal if we followed the left hand side, but if we followed the right hand side, we could have come here, then we said okay, this is not, then we move toward this direction. So it's mean that it all depends on the selection of whichever direction you want to follow to reach to the goal. So okay, let's take this example which will clarify a bit things a bit further. So as I said that I can move from left to right, or I can move from right to left. But let's take here an example where we assumed the same concept where we said that we will move from left to right. So here you can see that I start from A and the goal node is B. So based on our assumption, so this is our right path and this is left. So I will not go to this path. I will keep on going to this path. Again, at this point, right or left, so I keep on going to this path. But I know that this is all this is not the goal. So the next step would be to move in this direction. When I reach this point, this is towards the right and this is towards the left. So I keep on exploring this path. So if I keep on exploring this path, this is not goal. Then finally, when I move toward this, so it's mean that I moved all this to reach to the goal, right? So it's mean that I need to traverse this whole thing to reach to the goal point. However, if in this specific case, but you know that the path was actually this one, but we explored all this. So in this specific case, if for example, we choose right to left. It's mean that this is left and this is right. So if, for example, we have chosen that if you take this example, which is more clear. So if, for example, I moved here, so instead of going toward this direction, I moved into this direction towards right. So it's mean that I moved towards right. When I came here, again, there was no other option I need to go. So in this case, you can see that you have only took 3 steps to reach to the goal. However, in the previous case, you took 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 steps. So it means that depending on whichever logic are you going to use, it can be different based on the problem that you have been given. That's why we call this as a blind search, because we don't have any logic, and when we just move from left to right or right to left, but based on our assumptions. So it can be the case that you can see that in this case, moving from right to left was lucky. It found its goal immediately. However, moving from left to right was a bit unlucky, and that's why we say that in case of depth first search, your solution is not always optimal. Now, here is another example, very good example to visualize depth first search. So if S is the starting point, normally if you are not given any starting point, then S means the starting point. So S would be your starting point even in the exam, and G represent your goal. Okay, so if I say that the goal is to reach to G from S, so your question is that what path would depth first search return for this search problem? So imagine that you are solving this problem with a depth first search. So what would be your outcome? What would be your path? Who's going to tell me that if I start from S and my goal is G, so what would be the solution for depth first search? If there are multiple paths leading to the solution, we know that the algorithm will stop as soon as it will get its first solution. As mean the first solution path that would lead to the solution would be the path of the algorithm. It will not go to any other path if, for example, it has found the path in the first go. So what would be the path here using depth first search? Starting from point S. Who's going to tell me this? Take your time and find this one. You know that we simply need to move towards left or right, and we're going to go towards the goal. So from S, should I move toward A? Should I move toward this direction or this direction? Direction number 1 or direction number 2? From S, based on depth first search, should I move towards direction number 1 or direction number 2? Yes. So no, how is this number 2 burnout? We said that we always look at left and right of our hand. So if you look at your hand, the left side would be this one. So it means that from S, the very first thing that I'm going to do is move towards the left hand side. So it's mean that I will be going to move towards 1, not towards 2, based on depth first search. Yeah, there was a possibility that I move towards G. If I followed that, I need to go towards from right to left. But as I said that if there is nothing mentioned in the question, there is nothing mentioned. So it means that you always need to follow from left to right. This is very important assumption. Okay. So it means that we're going to move from left to right. So the very first thing was to move towards A. This was the most logical thing that I can do. So if I do all this in terms of frontiers, which is more understandable. So the very first thing starting point is S, but S is not frontier. So next thing is that The first thing was S. S is not frontier, so the frontier is empty. So I need to add the next node into this frontier. So the next node could be B or C. But as I said that we will see left and right, so we will write it as B, C. Now, as I said that the extreme left would be taken out first, would be judged first. So it means that from A, I will move towards B and would see if B is the goal node. No, B is not the goal node. So it means that, so here S was not the goal node and here B is not the goal node. So it means that whatever would be here would be left is the C. So it means that now I'm at the B point. So from B point, there is only one node left is D. So it's mean that now in the frontier, I would be having D, C. And now it's mean that I need to take out D first. So I will come from here, I will come to D point. Again, D is not the goal node. From D, so it's mean that if I move further and C, D is not the goal node. So in the frontier, it would be C left. And then finally, I will expand the node. So while expanding the node, I need to add G towards the left of C. So it means that again, which node would go and would be explored first? It would be G, which would be explored first. So when I come here, I explore G, so it will say, okay, G is the goal node. So if I say that which path depth first search would follow, depth first search would follow S to A to B, B to D, and D to G would be the path for best depth first search. However, if we could have chosen right to left, so the very first path was, if we could have chosen right to left, so the path was S to G. But here we have said that no, we will be using extreme left until there are no child nodes. So that's why we said that okay, this is the path. And as I said that the algorithm will stop as soon as it will find its solution. So you can see that there was one path, this one for towards the solution, but there was another path which is S to A to C, and C to G. But as I said that the algorithm already found a solution, it will not go to the another path. Okay, here you can see that in this example, you can see that there are some numbers mentioned here, which are path, mean how much is the path cost. We mentioned what is path cost, but for the case of depth first search, these numbers are nothing because depth first search is a blind search. It will never look for the path cost. So if, for example, you see here, mean the path which was given by depth first search, if I count 1 plus 1 plus 3 plus 3, this would be 7. 7 plus 3 would be 11. So you can see that it's charged me 11 points to reach to the G goal. If, for example, I followed this path, so 1 plus 1, 2, and 2 plus 2, 4. So if I followed this path, it would have given me 4. But as I said that depth first search doesn't look for path cost, it just blindly search until it finds a solution. And since it found its solution in going to the first depth, so here you can see that it went to the solution. As soon as it reached its first depth, it will never look for the other path. So that's why if you're given an example and ask you that find the path, you can find path in this way. And if you are asked to show some work to how you reach to this path, so you can show this in terms of these frontiers to reach to the goal, and this is how you will get full marks. And this is very important and key example. Right. So the first search that we just explored was okay. So the next algorithm that we going to study is breadth first search. Sorry, my bad. Right. So no, so this was depth first search, where we were going to towards extreme depth, and the next search that we're going to look at is breadth first search algorithm. So from its name, we can see something that we will not going in a one go to extreme depth, but we will be taking breadth at each node, and we go at each level we're going to search all at once. So it means that we are not going to go to the end of the algorithm, but breadth first search will follow. So in this case, what we're going to do, we will follow multiple directions at the same time, taking one step in each possible direction before taking the second step. So it means that if we see it, so it's mean that so it means that if we take the same example A, B, C, D, E, F. So it's mean that in the case of breadth first search, we move towards the depth first search, we move towards the depth, right? This was the depth first search, and then we move towards the next point. But in case of breadth first search, you will not be going toward the depth. What we're going to do, we move from A to B, then we move from B to C, then we move from C to D, then D to E, and then E to F. It's mean that what we're going to do, we in at each level we're going to search all nodes. Then at each level we're going to search all nodes. So it's mean that instead of going towards the depth in one direction, we will be exploring nodes at each level. So we will be taking one step at a time. So that's why we say that a breadth first search algorithm will follow multiple directions, not only one direction at the same time. Here, the important thing that we need to see is last in, first out. So this is what you need to remember. In the previous case, if you remember that whenever we were having, so if for example here was C, so we keep on adding things on the left, so that if for example I add for example D here, so that I can take D out first. So that was first in, first out. But here is last in, first out. We're going to see that how we're going to achieve that. Okay, let's take the same example as we have done in the previous step. So here we have to find a path from A to E, and here, as I said, goal is E. So the very first step again is the same thing, that we start with a frontier. We're going to add the initial node. The initial node is point A, and we're going to put it in the frontier, and we will see if it is a goal node or not. And as we all know that in this case, the goal node is point E, so this would be sent to the explore set, and we will keep on expanding the node. As there is no other possibility, the only possibility from here is to B, so we will be adding B to the frontier. And again, we're going to check if B is a goal node or not. But from here, you can see that now we have two possibilities. We have C and D that we can take. Again, as I said, we have two options. We can first move towards D and then, but for the same logic as we have done previously, we will start with towards D. We will start from the left and okay, so we will start from the left. So while so you can see that next or CD. So we will simply write. So we will simply write C and D here. So you can see that we have written C and D here. Okay, so now in this case, you can see that we mean there is no mean previously this list was empty, so we simply came to CD. So now, as I said, that we can go from any direction. So in this case, we can choose anything to take out. So we will go towards C first. So you can see that we move towards C. C was not the goal node. Now we need to expand the node, right? So the next node that we can expand is E. But as I said that in this case, I don't want to go into the depth. I want to move towards D first. So what I'm going to do, I'm going to write E here. Why? Because so that I can take this node which is on the extreme left. So in this case, you can see that uh, in is towards the last, whereas out is the first. So you can see that last in, so we are putting it in the last, but we are taking out the first one. So that's why you can see that we put the expanded node towards the end, but to explore which will we going to explore, the explore would always be the extreme left. So you can see that we're going to explore whether D is the goal node or not. No, D is not the goal node. So again, we need to expand it. So the next immediate node is F, but as we know that we move from here to here and here, the next step would be to check this one, not the immediate next one. So again, what we're going to do, we're going to add F here so that the next expanded node should be E. So you can see that again we have added last in. So the the in the the input to the frontier is towards the end, whereas the out would be first out. So but out would be the first thing. So we're going to check the node E. So you can see that here E is our goal node, and we'll say that okay, we have found our solution. So we move from A to B, B to C, C to D, and D to E. So this is another kind of algorithm that we use, and I would say that this is more this is a better algorithm than the depth first search, because in this case, um, if for example the goal was D, so you can see that it keeps on checking each level rather than going to the depth. So it is possibility that it can find algorithm quicker. However, again, since these are the blind search, so there is a possibility that it can take more time to find the solution. If, for example, your goal was F, so this could have taken more time. Again, going towards the same example which you have done previously for depth first search. So we know that for depth first search, we came to this point, then we came to this point, and then we came to this point. So finally, we said that our solution was this point. So this was for depth first search, right? We keep on going towards the depth of the algorithm. But for the case of breadth first search, we move in both directions. So if I put it here, A, B, C, D, E, F. So I move from A to B, B to C, then C to D, then D to E, E to F. So it means that I take one step in each direction. I take one step in each direction. So again, starting would always be moving towards left. So this would be my first step, but if I take this example, which is A, B, C, D, E. So if I take this example, my first step would be to move towards B, and then the next step would be towards C. Or indirectly, I can say from the initial point, my first step is to move towards B, and then the next step is to move towards C. So you can see that the next step I took is towards in this direction. So it's mean that so these were the actual directions. So the very first step was to move towards B, and then the next step was to move towards C. So it's mean that indirectly I can say that the next search point was towards C. Similarly, the next would be to move towards in this direction. So again, I move from B to C. Indirectly, I can say I have already explored B, so I can say that I move further towards D. But at the same time, from this D, I move towards E. So it's mean indirectly I move. So each time I'm taking step in both directions, then I will take step in this direction and this. So from here, you can see that I immediately will reach to the goal node. So you can see that I moved in this direction, then this, then this, then this, and I finally reached to the goal node. So it's mean that this algorithm was much promising than the other algorithm, because we take step in each direction. There would be another step here, and then at the same time we have step. So when we take this step and finally we move towards this direction, we'll see that we have found our goal node. So one step in each direction at a time. Okay, so this is the same example that again we have done for depth first search. We start from this point. I have omitted some initial slides. I don't know, maybe they're deleted or something, but we start from the beginning. So if we start from this point, so originally these were white, so we move toward this, this, until this point we were not having any option, but when I reached at this point, from this point I will move 1 point here, 1 point here, then 1 point on this direction, 1 point this this this. I keep on moving in these directions. You can see that I will keep on moving in both directions at the same time, and this is how I will reach to the goal. So in this case, you can see that it was the same example, but we have moved in both directions at the same time. So there's a possibility that we reach to our goal immediately. I will. There is some animations missing here, so it should start from a white and then keep on moving. I will rectify this and upload it to the PLE. In case of breadth first search, at each point we stop, we take a breath, we move to once towards right, towards left. Then here I will take a breath, I will keep on moving, and I will also keep on moving into the other direction. Now, as I said that these blind algorithms they are not very accurate, so they do have certain issues. So if we talk about the depth first search, as I said that if your goal is in the first depth, then it could be the fastest algorithm, right? If your goal is in the first depth, it could be the fastest algorithm. But however, if it is not lucky enough, if your depth is toward the extreme right side of the tree, then it could be the most expensive one. So that's why we say that the solution that we get from this is not always optimal, and in the worst case, the algorithm will explore every possible path before finding the solution. So it means that if you remember the example where we started from A, B, C, D, E, F, G, H, J, K, L, M, M is the goal point. So you can see that it was the extreme left point. So it traversed all the paths which were redundant paths, which we did not want it, but we have to traverse all those paths to reach to the final point. So that's why we say that solution is not necessarily the shortest or least cost path. So if you remember, we done this example. If you remember, we had done this example. So in this case, we said that the depth first search was finding this path, but if somehow we look at the cost, so you can see that this is not the this is not the shortest path, not in terms of cost or anything. So that's mean that depth first search, these are some issues with the depth first search. And as I said that previously, we sort algorithm with respect to several things. One is completeness, whether it can find a solution or not. Yes, it can find a solution, but then time complexity. So in this case, we say that it can be lucky enough, but it can be more time taking. Okay. And here there is something that if goal may be at level D. So if you remember, I was having B, C, D, E, F, G. If, for example, your goal was E, and if I take it level 1, level 2, level 3, level 4, although you can see that your goal is at level E, but it will go to first depth and then it will come to this point. It means that although your goal was on level E, but it will go towards the depth, which by its nature. However, if we talk about breadth first search, so breadth first search will come here, 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 and finally it will reach to the goal. So it means that instead of going to level 4, breadth first search will reach to its goal at level E. However, for depth first search, the complexity is different. So that's why we say that if you have B number of branches and if you have total m number of levels, so your complexity would be measured as B raised to the power m. So if, for example, you have 4 branches and total number of levels are 3, so your complexity could be this much. So that's why we say that normally complexity is denoted by parameter O, and in the brackets we write the complexity function. So it means that depth first search could be very much complex if we have very deep tree, because it will go to every possible depth. Right now, coming towards the breadth first search, we say that this algorithm definitely find a solution. So it means that it is a complete algorithm. At the same time, it is simple to implement, and it can find the shortest path. But at the same time, if, for example, your goal is lying at the extreme right, again, it can take, because it moved from one level, then from different nodes on the same level. So it is possible that it can take extremely large time to reach to its final point. So both of these algorithms, we will not say that they are perfect. It depends on where we're going to use them. But overall, if we say that how we going to if I summarize, so you can see that in case of depth first search, we will move toward extreme left, then we will reach to neighbor, then we go to the next point, then we go to extreme left, then we will move to its neighbor, and this is how the depth first search works. On the other hand, if you want to see how a breadth first search works, so the breadth first search is that we move to left, then we go towards right, then another left, right, and this is how you keep on moving from one point to the another point. So here the good thing is that you can see that it came to the left, then it moved towards right, then again left, then right, then another right, then another right. So if you can see that on the same level, it is checking all the possible. So here you can see that on the same level, it is checking all the possible nodes, and then it is moving towards the next level. And similarly, you can see that it is moving towards, it is checking all the possible nodes and moving towards the next level. Any questions so far?
So,
Okay.
when does the last in first out come into play on the breadth first search? Yeah.
So the last in
first out. When does it come into play on the chart? If you go back to, if you're moving it, yeah.
Here,
on
right?
the method. How would you describe the last in, first out?
Okay. So if we give some names to states, right? So we start from node number A. If, for example, we say that, let's say G was the goal node, let's say. So A is not the goal node. So the next possibility is that in the frontier, we have B and C, right? At the moment, we don't have, when A was not the goal node, the frontier was empty. So that's why we simply added B and C in the frontier. So now in the next step, we're going to check whether, so now you can see that whoever is the first will get out. So LIFO, first out. So first out means the very first thing will come out. So we're going to check if B is the goal node. No, this is not the goal node. So we will write frontier as C. Now, the last in will come in. So we need to expand the node, right? So if we see from when we reach to this point B, the next possibilities are D and E. So it's mean that we need to expand. So it's mean that C is already here. Now we are at point B. From B, we have two options, D and E. So we're going to put D and E here. So that, so here you can see that the input was in the end. So last in, so we're going to put whatever we're going to input to the frontier will go to the end, last in, whereas the thing that would be out would be the first out. So that's why you can see that the next thing now, the next thing that I'm going to check would be to check C. C is the goal node or not. C is not the goal node. So now again, I have D and E in the frontier. So that's why you can see that when I came to point B, the next thing I checked was C. So that's why it was the C. So here it comes, it says that whenever you're going to whenever you're going to put something into the frontier for breadth first search, you're going to input that thing in the last. But you're going to take for checking whether it is goal node or not, you're going to take first out. So that's why in the other case, for it was first in, first out. So it's mean that you're going to in on the first side, and you're also going to take out the first one. Okay.
Oh, okay. Yeah, thank you.
We'll take 5-minute break, and then we're going to start this uniform cost search. Okay, so we will move a bit further and would see that what are other search methods. So the very first that come in is called uniform cost search. By its name, you can see that in this case we have a factor of a cost. So it's mean that we will not be spending blindly, but we will be using cost as a factor for deciding on in which direction we should move. So that's why in the previous two cases that you knew that how we were listing a node into the frontier was either FIFO, first in first out, last in first out, breadth first search, sorry, depth first search, and this was breadth first search. In this case, what is queuing function? So in case of uniform cost function, the queuing function is the cost. That what is the cost? Based on the cost, we're going to decide whether we're going to which node we're going to take. Now, how are we going to define cost is if, for example, this A is our initial node. So, and B and C are any other nodes. If, for example, we are at node C, so cost at node C, which is G at C, what it would be equal to? It would be equal to all the cost from the initial node. So if, for example, this is 1, so I can say that cost to reach node C is 1. However, if we have another node D here, and if here the cost was 2, so if I want to find how much is the cost to reach node D, so it would be 2 plus 1 because the cost is usually defined as the sum of the costs from the initial node to the current node. So this is how we're going to find the cost. So it means that the queuing function is sort by cost so far. So whichever point we are, we're going to look at the cost. So if, for example, I am at point A, so I will look at the cost. If, for example, this is 2 and this is 1, I will move towards C. And then again, I will look that whosever cost is lower, we will going to move to that first. So it means that first goal that found would be the least cost solution. Why? If, for example, we are only following the nodes, we are only jumping to the nodes for which the cost is low. If, for example, by chance moving towards that node, we're going to find the solution that would be our least cost solution. Why? Because in any case, the path we were following, we were choosing that based on the cost. So if we have solution in that path, that would be the least cost solution. So let's take an example, and then we could read it again, or you could read it again, and then it would make more sense. So now here the goal is to reach to Bucharest from Cebu. So this is our goal, and we need to see how we're going to move. But before that, it's very important that we need to know how much is the cost from one node to another node. So let's we are taking this example where we know the cost that if, for example, we are moving from Cebu to Figueres, this would be the cost or distance from one node to cost from one node to the another node. So how are we going to move forward? So as I said that in this case, the main goal is to look for the cost. So when I started from Cebu, I came to know that I have two options. I have an option to go to Reminico, which is for which the cost is 80, and I can go to Figueres for which the cost is 90. So based on uniform cost search, what was the queuing function? The queuing function was sort by cost so far. So it's mean that if I want to see the frontier, so I have two things. I have Ruminico for which the cost is 80, and I have Figueres for which the cost is 99. So I have sorted them. It means that the lowest cost is for Raminico. It means that from Cebu, I'll move to Dominico. This would be the most logical step based on uniform cost search. It means that now I am at this point. The next step is to explore further. So when I reach to this point, the next thing is to go to Pitisti. So it's mean that but at each point I said that I'm going to find the cost. So the cost to reach to P point would be the sum of 97 plus 80. Why? Because at each node, the cost would be the total cost from the initial point to that node. So it's mean that in this case, the cost is P is 177. So it's mean that from reaching to Cebu to this specific node P, the cost is 177. However, at the same time, you can see that now the cost from Cebu to Fagras looks smaller. Then instead of going towards point P, going towards F seems smaller. So it means that at each point, we're going to look for the cost from the initial node to the certain node. So at the moment, there were two nodes which we can see. Initially, we saw R and F. So R was lower. Then we moved towards P, but reaching to P was more costly than going towards Fagras. So it seems that it makes more sense to move towards Fagras. So we move towards this point. Now, from Fagras, the next point is Bucharest, right? So if we going to add the cost, so it would be, so if we from here, if you want to go to Bucharest, it would be 99 plus 211. So it means that the cost would be 310. But at the same time, we also going to see the cost on the other side as well to see which side is better. So if I want to reach to this point from on this side, the cost would be 80 plus 97 plus 101, which is 278. So it's mean that I will not proceed further from Fagras to Bucharest, but I will suggest that my algorithm based on uniform cost will suggest that I need to follow this path. Why? Because this path is the least cost path. So that's why in uniform cost search, at each point, the algorithm will look for this. How I mean, if we take an example of map, so you will find different, it will find different paths and then will give you the path which will result in least cost. So you can see that this is how the uniform costs work. At each point, we're going to find the cost of the path, and then we will decide that in the end, we will decide that which path is most suitable. So in this case, the path which is suitable is this one. And here we say that uniform cost search is complete. Completeness means that it will definitely give us a solution, and this is optimal. Why this is optimal? You can see clearly that it will always find the path which is a least cost path. Here is another example. You can see that the goal here is to reach to point S from G. So this is your example. So you need to reach to point G from S. If we could have followed breadth first search or so on, then things would be different. But here, what we're going to do, we're going to use the uniform cost search. So you can see here that we'll start from certain point. We start from S. For example, we started from S. So what was the possibility? The possibility was to go to A, to go to B, to go to C. But which way we should follow? Based on uniform cost search, we will follow the path which has lowest cost. So at the moment, it makes more sense that I move towards A. Why? Because here the cost was only 1. So it was making more sense. Why? Because it wasn't making sense to go to B or C because the cost was higher. Now it's mean that I'm at point A. I need to expand it. So if I expand it, it means that if I could have expanded it, the cost, the total cost would be G would be 1 plus 10, which is 11. But at the same time, I will not expand it at the moment. I will first check the other things as well. So what if I, so at the moment you can see that instead of going towards G, at the same point going towards B is less costly, because going towards S to G gives you 11, but at the same time there is another node which is less costly. So at each point, because we don't know, we visually we can see that yes, Bucharest is our goal, but if you see from the algorithm perspective, it doesn't know until it do the goal test. So at each point we'll be doing each node, whichever node is less costly. So here you can see that from S to G is most costly than from S to B. So that's why you can see that we left this here and we move towards B. So when we move towards B, this was 5 and 5 was less costly than 11. So the next thing is to expand it. So if we expand it here at this point, you can see that G would result in 5 plus 5. It means that G is resulting in 10. And we already know G is goal as well, right? So it means that if I could have moved from S to A and A to G, apparently in the first step, S to A was more logical, but then A to G was expensive. So that's why the algorithm will discard this path and algorithm will go from S to B and B to G, because algorithm will look for the least cost path, and that's why instead of going from S to A and A to G, we directly went from S to B and B to G, and which we can see from here as well. But for the algorithm, this is very easy example at the moment. Looking at, we can see that, but for complex example, we need to train the algorithm based on these methods. Moving further, so this is very good example, which is a bit comprehensive as well to give you an idea. So here we have to reach from C, which is the initial point, to the goal, which is Z, and also there is another goal which is C, goal C. So you can see that the one which is double circled, this one and this one, is both of them are goal. But as we know that these algorithms stop as soon as they find the first goal with the least cost path, they will stop it. So that's why here I have written it as goal to C. We'll see it in a while. So what would be the logical steps to move towards the goal? At the very first thing is to look at the cost. So you can see that here it is 2, it is 1, it is 3, it is 2, it is 5. So it means that the very first logical step is to move towards T. Why? Because this is the least path. And as we said that we do it how? We do it by sorting the by writing the frontier by sorting the cost of the path. Sometimes frontier is also called open list. So in this example, you can see that I have written here as an open list, but this is frontier. Frontier and open list is the same thing. So while attempting an example, the very first thing is to start from a certain point. So we started from tier C, and as we know, this is not the goal state. We will move further. So what are the further options? The further options are B, T, 0, E, P. These are the further options. So these are highlighted in green. But what we have to do, we have to sort them based on their cost. So this open list should look like this. T1 should be in the first, then 2, then O3. But before O3, there should be E2, O3, and P5. So it's mean that the very first thing was to write the frontier with all the possible nodes, but at the same time with their cost, so that it is easy for us to decide which way to go. So from this frontier, I can clearly see that T1 is the most logical step. So why? Because it has least cost. So my aim would be to move towards T. I moved towards T, which is highlighted in red, but I came to know that the T is not the goal node. So it would be taken out from the frontier and it would be added to the explored list. So explored list would contain T1 because this was not the goal state. Now you can see that in the open list, what are different options? In the open list now, T1 is taken out. What is left behind? The left behind is B2, E2, O3, P5. So it means that this was not the path. So the next step is to choose something. So here you can see that E2 and B2, they both have the same cost. But again, in such cases, we have to decide on something. So in this case, as we always say that we will go towards the left side. So it's mean that we will move towards B2. When we came to B2, now at the same time, you keep on looking at the cost. So now you can see that since we move from C to B2, so the cost at B2 is 2. But B is again not the goal node. And from B, what are different possibilities? From B, the possibilities are A, R, S, O, E, P. Why? Because we need to see whose cost is less. So that's why we say that the possibilities here are A, R, S, O, E, P. But we need to look at the costs. So, and we need to write the frontier. So it means that if I want to reach to A, so cost of A would be 1 plus 2. Because cost is calculated from the current node to the initial state. If I want to write R, R would be 4 plus 2. If I want to write S, it would be 3 plus 2. Similarly, if I want to see O, for O, I already know it's O3, it's E2, and it's P5. So if I sort the frontier, you can see that A is 3, O is 3, E2 is E2, S is 5, P5 R6. So from here, if it was a depth first search, I could have moved towards A, but this is not depth first search, right? This is uniform cost search. So it means that I have to go towards the minimum cost. So what is here the minimum cost? The minimum cost here at the moment is E. So it means that I will move towards E. And again, you can see that since I move towards E, so again, your cost at the moment still stays 2. Why? Because E was 2. But at the moment, you can see that E is again not the goal node. So it means that what are the next possibilities? Next possibilities are G, O, A, R, S, P, because these are the next possibilities from E, because these are the unexplored nodes. From E, you can see that B is already explored, T is also explored. So A, R, S is left. From E, O is not explored, so I cannot go to IN. P is not explored, so no possibility for L, F, and D. So it means that the next thing that could be possible is P, G, O, A, R, S. But again, I need to look for the cost. I already know cost for P, it's P5. I already know cost for A, it's 2 plus 1, 3. For R, it's 4 plus 2, 6. For S, it's 3 plus 2, 5. For G, the cost is 5 plus 2. No, so sorry, for G, the cost is, yes, for G, the cost is 5 plus 2, it's 7. Okay. So it's mean that looking at in here, O3, A3, S5, P5, these are the possible options. These are the possible options that I can take. So now you can see that O3 and A3 has the same cost, but at the same time, I know that A3 is on the second level, where O is on the first level. So it makes more sense to finish with the first levels and then go to the 7th level. So that's why from E, I will jump towards O. So you can see that from E, I jump towards O. But again, O is not the goal node. O is not the goal node. So it's mean that what are possibilities from O? From O, again, the possibilities are A, R, and S, P, G, and there are two more possibilities now, which are I and N. So it means that from O, I can go to P, G, N, I, A, R, S. Let's find the cost again. For P, I already know. ARS, I know. For G, I know. I need to calculate for I. I is 3 plus 1, 4. And N is 2 plus 3, 5. So if I look at this list, you can clearly see that A is the winner because A has the least cost. So it makes more sense to move from O to A. So we will move from O towards A. But again, A is not the goal node. So from A, what are the possibilities to move further? The possibilities to move further are either R, S, I, N, G, P, because there is no further node towards A. So these are already existing possibilities. But I need to look at the cost for all of these. So you can clearly see that I4 is the winner because I has the least cost. So I need to move towards I. And now from I, you can see that I can move towards Z, R, S, N, G, P. But again, I need to find the cost. So you can see that if so again, you can see that if we want to see the cost, so P has 5 cost, I has 3, 1, 2. It has Z has 6 cost at the moment. S has 5 and so on. So it means that I have to move to something. So again, as I said that since P5 and S5 has the same cost, but P is on the upper level, so it makes more sense that I finish the upper levels and then I move to the lower level. So that's why I move towards the P. And after this, again, I need to find the cost. So you can see that S is 5, remains the same. N is 5, R is 6, Z is 6, for F you can see that 1 plus 5, 6, D 3 plus 5, 8, G is 5 plus 2, this is 7, and L is 5 plus 5, 10. So now you can see that I have S, I have N. I have these two options from P to move. So it means that again I need to decide on this, and it makes more sense to when we have equal chances for something, then we have to decide on some rules. And we already said that we will go towards left. So it makes more sense to move towards S. When I move towards S, again, this is not the goal node, so I need to look for the other thing. So at the moment, I can see I have R, I have N, G, L, F, D, Z, these are possibilities. So again, I need to look at the cost. At each point, I need to find the cost for the node. So here I know that the cost for the node N is the least, which is 5. So from S, it makes more sense to move towards N. So I move towards N. When I move towards N, you can see that I can move. I can again calculate the costs. I can again calculate the cost and look for the. So you can see that from here, when I calculated the cost, I came to know that I have Z6, I have R6, I have F6, and so on. So here you can see that if I move further, I can see that if I move to Z6, I can clearly see that Z6 is the goal. But at the same time, we clearly see that before going to Z, there are possibilities for R and F. And since we said previously that we finish with levels first and then we move to the further, so before going towards Z, we will first go towards R, then we will go towards F, and then finally we'll go towards Z. So here, finally we move towards here and we find the Z. But before exploring these, we will take out R6, we will take out F7. So this would be in blue color, this also would be in blue color, and then we move towards Z. So it's mean that we move based on the cost. If there is a tie between certain things, then we will decide whether it is on the upper level or lower level. And if we have tie on the same level, then we will move towards the left. And this is how we move to forward and keep on finding the goal. Overall, you can see that when I came to the goal, the cost was 6. So it means that this would be the path for that I'm going to use based on uniform cost search. But of course, to reach to this path, there was so many other routes that I have taken, I have searched out, but finally I came to know that this would be the best path that uniform cost search would return finally. But to reach to that path, there were many other things. So the cost for this path is 6. So it's mean that goal is found, and to reach this goal, the cost of the path would be 3, 1, 2. So this would be the best path. And if we keep on moving, we can go to L as well, but we definitely know that since we move to based on the cost, so moving towards L would be more costly. So that's why Z is our best solution, best cost solution for the path. So although uniform cost search is also categorized as the uninformed search, because here we just looking at the path, but there are some other parameters that we need to look at, but those will fall when we're going to study about informed search. Any questions so far? Right, I think no question. Okay, so and we will start this informed search hopefully in the next lecture, because we don't have enough time in today's lecture. After 10 minutes, we're going to start the workshop, and we're going to use Colab. As for your first test is concerned, I believe everyone has received their marks. I have uploaded them to VLE. If any, I mean, I was planning to give a feedback in today's class, but because of tube strike, it wasn't possible. I will bring your exam papers next week. You can go through it. But in the meantime, if anyone has any question about their marks or want any feedback, please let me know. But I will definitely show you your exam papers in the next class, so that you should see. And if there is any query or any point that you want clarification with, I would be more than happy to provide. Hello everyone. I have uploaded the workshop sheet to the VLE. You all will have the access to it. I have Ali in this call, Ali Hamza. He going to introduce you about the lab, and then from the worksheet, you're going to do the steps that have been mentioned. Overall, I would explain that you are going to use Colab for doing Colab for Python, and you will be following some instructions. For example, you will be introduced to some basics of Colab, and then what are different libraries that are useful for later on implementing the AI algorithm. So most probably we will be covering only the important libraries, and then I will also be uploading some of the notebooks, Python notebooks for these different search algorithms, but those will be optional. For the sake of this course, we will only be covering Colab, how we're going to use it, what are different libraries, how to explore those libraries, and so on. So I will hand over to Ali now. He's a research assistant in the School of Engineering, and he's assisting me on this. Um, can you please all open your VLE and check if you can see the file? Ali, you can share your screen if you want, and you can start now.
Okay, sir. Thank you so much. Can you all see my screen?
Yeah.
Okay, well, let me introduce myself. I am Ali Hamza, and I am a research assistant here at the School of Engineering, and I am doing a PhD in machine learning under the supervision of Dr. Zunaib. Okay, so I will tell you about Google Colab. So what is the Google Colab, and what are the basic function of the Google Colab, and why we are using the Google Colab when we are dealing with the machine learning and the Python. So I will just tell you about a basic of a Google Colab, that what is the Google Colab. Actually, the Google Colab is a document that is built by the Google that allows you to write, run, and share a Python code. If you are working with the machine learning, and if you are mm, trying to make artificial neural network for any of your requirement, then you have to write some codes, and for that we are using the Google Colab. Well, if you people are familiar with the Jupyter notebook, so exactly what is the Google Colab is exactly the like of a Jupyter notebook, but uh, this is come in a Google suite of tools. For the Google Colab, we actually don't install any kind of a software, which is a basic good thing about the Google Colab. So let me tell you about a little bit a Jupyter notebook. Actually, we use a Jupyter notebook mostly for if we are working with a Python, or we are developing some kind of a codes and all this stuff. So the Jupyter notebook allow you to create a document containing the executable code along with the text, image, HTML, LaTeX files, which you can store in your Google Drive. Okay, instead of using a Jupyter notebook, we can use our Google Colab, which is a simple. We can use it in any browser, like you can use it in a Google Chrome. And on Google Colab, we can use different deep learning libraries, which are the PyTorch. If you are working with the open source software library that can give you an interface for the artificial neural network. So we can use different libraries such as PyTorch. So Keras is also open source library that is used in our Google Colab for a computer vision library. Similarly, for the object detection and for the building artificial neural network, we can use the TensorFlow and the Open CV. So this is a little bit uh, 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 introduction about a Colab. So the other main feature of the Google Colab is it is like exactly like a Jupyter notebook, but it is hosted by the Google. So when you are working with the Google Colab, so you have to required our Google account, which is your Gmail account. So for that, we do not use any kind of a software. So no installation is required. So you just simple open the Google Chrome and you just type the Google Colab and the all Google Colab environment is just come on. Okay, actually, due to no installation requirement, so the network speed is very high. It's very good, and we can write any Python code inside the browser. And after finishing our Python codes and all of this stuff, and we can save that file in a Google Drive. We can use the Google Colab for building artificial neural network for the deep learning libraries and for the data science library, which is already built in libraries, and we can use it for our system. Also, the Google Colab come with the GPU, CPU, and the TPU support, which actually we use it according to our system requirement. Okay, so I will tell you that how you can access to that Google Colab and how you can start with the Google Colab account. So these are the some kind of uh, instruction. First, you have to log in to your Gmail account, and after that, you can search. Just open the Google Chrome and search it like Google Colab. So here we get here comes the welcome to the Google Colab. Just click on it, and it comes with a Google dot collab.research.google.com. So when you click it, so this window will appear on it. Actually, I'm working with the Google Colab. So these are my notebook files. You will come again with that kind of a window. So you can just click here and to create your new notebook. So this window will appear on your screen. So this is the Google Colab environment. Actually, it's a platform where we can write a Python code. So this is called a cell window where you write your different cell, different codes. Okay, so the first step we just did, and again after that, select a new notebook to begin a new document. Alternatively, to create a new document from any screen, just select file in the top left corner and then select a new. Actually, these are the instruction which you can follow by doing when you are just open the Google Colab and just developing your new Google Colab team. Okay, so from that we can change the name of that file. Just click on that name and you can just name it anything like my, I just give them my notebook file. Okay, so after that, to run that system, you should go to the runtime and just click on that change system here. We can say that it comes with the hardware accelerator. Now it will use your computer GPU and TPU. Now it's depend upon that the system contain a GPU, CPU, or a TPU. So normally we select the GPU for that and just save it. Okay, and after that you should connect it with your Google Drive along here. And so in a cell you can write anything. Just I am trying to if I want to print something like that. Okay. Okay, so this is called a run cell. After writing your code here, you can just click on that cell and it will just run your Python code here. Okay, so after when you finish in one cell, you can go to the other cell by just click on here like a plus code. Here you can print anything like I'm just putting the any integer value like that, and it will print an integer value like 8. Okay, so when we put these commas, so this is called the string, And for the integers, we don't have to put that comma for that. Okay, so some other code that I am writing. Okay, if I have a two numbers, like suppose I am I I have a number 2, so I am assigning it to the um, variable a, and there is some other code, other number, so like that, and I want to sum it. So you can write as such: sum is equal to a plus b, and okay, just run it, and now print it. So it will give the final result of the these. So these are basic just code, and that you have to write inside these cells. Okay, so with the code, there is a new window come, add a text file. So you can add a comments to your code also, like that code was about that how to sum the two numbers. So I must say the adding of two numbers, and just and shift plus enter. So we can also add a command inside it. So these are all just the general steps that I already put in our document file. So you can then check it and try to run it all. Okay, so now we are moving toward the some basic function. As I told you that how we can write some basic Python codes into that. So I mentioned some function in this file. Here again, this is the sum file, and there are some of other instruction, like if you add some other code line, so you have to just click on a plus code, and if you want to comment on your code, so you have to click that plus text. Other than that, we have that kind of window, like you can also add a comment from here. You can delete that cell from your code if your code is not working, or you can face any kind of error in that, so you can just delete that cell from it. Okay, if you want to move that cell to the up and the lower side, so you can use that cell into up and like click on it, so it will just automatically go and up and side, depending upon that where you want to put that cell into your code. So this is just uh, basic things that we are doing with the Google Colab, Google Colab. Okay, so after that, after finishing your codes and after executing all your the result, you can save that file in your Google Colab. So just click on the file. Here we can save as a copy in a drive. So it will automatically save into your Google Drive. But please mention that you have to link your Google Drive with the Google Colab. So for that, we go to that window. Uh, Yeah, so for a Google Drive, you have just to save it in a Google Drive. Okay, if you want to download that Google Colab file, so here you can download it also, and download it in a IPYNB format. Actually, the Google Colab document come with a two format. One is IPYNB and one is .py. So this is the just the basic uh, structure of the Google Colab, and how you can run your all codes here. So if you people have any question that you can ask from it, after that I will go to some basic libraries and will tell you about some other functions that how we are going to put in Google Colab. Okay, so let's move to the main function libraries. Actually, I also put some link inside the Word document. By clicking that link, you can check simple basic Python codes which are being executed in a Google Colab. In that um, link, actually the some of the two numbers, the difference is how you can subtraction of two different numbers, multiplication, uh, division, that how you will divide the two numbers in a Python while using the Google Colab format. So you can just check this document and try to execute it by yourself. It's just a simple uh, Python course, so you can also do it by yourself. Okay, so now come to the NumPy. Okay, so this is a very important library. So it is actually used for the linear algebra and for the mathematical expression, that if you want to do some kind of a mathematical calculation, or if you want to work with the linear algebra, so you will use that library, NumPy. So actually the NumPy, so what is actually the NumPy is, so the NumPy actually is a powerful linear algebra library for a Python. So it actually used in almost every field when you are working with the machine learning. And for that we are using a different kind of libraries, which is a Panda and other these two also. So they are totally dependent on the NumPy, as because the NumPy is a main building blocks. Okay, by using the NumPy, we can do multiple function, such as if we are working with the matrices, so we have to use the NumPy library, because we don't because the matrices operation is not executed without the using the NumPy libraries. If you want to work on a different mathematical expression, like we have one mathematical expression and we have two mathematical expression, we want to add up, or we want to subtract it, or we want to divide or multiply that. So for that we have to use that NumPy library. Also, NumPy is used for plotting a different number of a graph. And also it we are using the NumPy if we are working with a different number of the list thing. Okay, so before going to the NumPy, so first let me tell you that what is a Python list that is generally using in Python. So for a Python list, actually the list are used to store multiple items in a single variable. Like we know that, so this is the example, the list one, actually we have the number of the fruits, so we have to put in that format, so it is called a Python list. Now if we want to just put some random numbers, so this is the in other list that we have. And if we want to write some Boolean expression like a true and false value in the list form, so this is the third list. So actually this is called a Python list. Okay, now uh, just write this list one, and in this form in Google cell, write this also and write this list in, and try to print it out and just check the result, that what kind of a result that Google Colab will show to you. Okay, so here we cannot use mostly Python list for our mathematical calculation, uh, because Python list is taking so much time in executing the results. Suppose we have these two lists, like suppose that we have list A, and these have one numbers like 1, 2, 3, 4, 5, and we have the list B, which we have the number like 11 to 15. Now I want the multiplication of the list A and list B. So just in a Google Colab, so you have to, so just write the list, like let me show you. Look, I am first writing the list A, and my list B is this. Now I want that I want the multiplication of these two lists. So for that, first run that cell. And now I want the multiplication. So for that, I am writing the print command and just writing the names of the list which I assigned to that one. Okay, so let's just run it. Look, now we are facing some kind of error because in a Python, when you are trying to do a multiplication, so the Python doesn't know about uh, this. Actually, the Python has no idea how to perform the calculation within the list. So in order to overcome this error, so we have to multiply the each element of the list A with the list B. So actually this taking a lot of time. So in order uh, to do the multiplication of a multiple list that we have in our system or a two list, so we for that we have to use the NumPy package. So the NumPy package is actually try to execute these the multiplication thing very fast, and also we are using that NumPy package to do these kind of a multiplication operation. So the NumPy is actually provide an alternative to the regular Python list. So instead of a Python list, we are now using the NumPy for these kind of uh, the multiplication operations. Using the NumPy, we can analyze the data much more efficiently than we can using list, and also it perform calculation over the entire array and in a very quick manner. So in order to use the NumPy package, so first we import the NumPy package. Actually, the Google Colab contains so many hidden package inside it. So for using that package, you have to first import these package from their internal repository. So just import NumPy as an NP. Actually, this is the library. If we want to work with any kind of that library, first we have to import it from the Google repository into our Google platform here. Okay, just okay. Now run this file. Now this blue tick shows that this code run successfully, and this library is just imported here. So after that, now we are using a NumPy package. Okay, again, we have a list A and we have a list B. So in order to do the multiplication of these two lists, we checked that by using the Python list, we got an error. So the Python don't know about how to do the multiplication of these two. So by using the NumPy list, we will do the multiplication process. And for that, we first convert these two lists into the NumPy array. Okay, so I am converting these two lists into the NumPy array by doing that, by giving that command. Okay, so this is the list A which is mentioned here, and just let me copy the another. Okay, so what I am doing here, I am converting the list A and list B first into the NumPy array, and after converting it into the NumPy array, I will do the multiplication process. So just run it. So now the green click showed that it successfully converted into the NumPy array, and after that I will print. I will use the print statement like this one, and we'll check now that what we will get by executing that command. No, actually the P in a print is a small alphabet. Look, now we come with that result in above. When I used to print, used to multiply a list A with the list B using the Python list print command. So actually we got an error here. I first convert the list A and the list B into the num array, and I assign the name of A and B to the list A and list B. And here when I use the command of print again into A into B, so here we get the actual multiplication of the two list. Here we can check it will multiply the each first element and the second element with each other. Like in a list A we have 1 and in a list B we have 11. So 1 cross 11 is 11, 2 into 12 is 24, 3 into 13 is 39, and so on. So now I think that you people now understand that why you are using why we are using the NumPy package and NumPy command in Google Colab. So these are other some print statement. So you can try it in your home, and actually it's a very simple. Just do it. Okay, so other than that, we now come with the nested list. So what is a nested list? These are some other kind of command that we are using in our Python code. Actually, these are all the basic libraries and basic command that when you work as a data scientist or you work on developing a neural network, so you will use that commands and that libraries in your functions. Okay, so these are some kind of other lists that are using generally in labs. So we will I will try to explain every these uh, command. So let me start with the first with the nested list. Actually, a list can contain any sort object, like we check in a list A and list B. And so the nested list actually contain another list within it, so which in turn can contain the sublist themselves. So this is actually the nested list, like this one, 2, 3, 4, 5, 6. So actually this is the main list, and inside the main list we have other sublist inside it. Okay, so if you want to run it in a Google Colab, so just assign these nested lead with any kind of your name. So let run this, just assign it with the NL and try to run it. I actually tried all these command in a Google Colab. So these are the window of the Google Colab. So you just simple write it as I mentioned here in as a list A and a list B. Okay, and after that, if you want to print it, just use the print command NL and it will give you result as such. Okay, so these are the nested list. And now if we check it with the numpy command, so first we convert the again nested list into the numpy, and for that we are using that command numpy.array. Any Python list for conversion into the numpy, we have to use that command inside it. So I am converting the NL into the array. So I'm using the npy dot array into L, and I'm assigning some other value into to them. So I'm assigning the NL1. You can assign any name into it is equal to numpy dot array and that nested lead. So it will give the result of this. So actually it shows that your nested list is converted into the array format. And if you want to print that, so again we can use the print command and write that into NL. So the nested list in array in NumPy format, it will show in that form. So you notice that the NumPy keep the shape of the nested list. Okay, so this is some other nested list. As we can see, that is the main list, and it contains the three different sublist in that. So first just print it and then convert it into the numpy, and then print it and just check that what kind of shape of the nested list that will appear in a Google format. So this is just the simple example. Okay, so that was all about the nested list and how you can convert the nested list into the NumPy. And before that, we worked on a Python list and how Python list we can change into the NumPy list. And after changing it into the NumPy, we can do different multiple operation like a multiplication, subtraction, addition, and the multiplication. Okay, so after that, now we come to the arrange command. So actually, what is arrange command in a NumPy. Actually, the NumPy arrange return evenly spaced values within the given interval. So actually, okay, so I have some numbers which is from 0 to 5, and I want to space it in a evenly space. So for that, I am using that NumPy command like np dot arrange 0 to 5, and when you enter plus shift it, so it will give you a result of this one. This will generate an array with a evenly spaced number starting from 0 up to 5, but it will not include the final uh, final word inside it. So it will give us the result up to number 4. Okay, so this is the another example that I have a range of numbers from 0 to 16, and I want to show it with an evenly spaced manner. So for that, I'm using that command np.arrange the 0 to 16, and when you try to run it, the result will come in that kind of a format, like from 0, 1, 2, 3 up to 15 value. Okay, after that, if I want to give the space of two values between the 0 and 16, so you have to write the number here. So this will show the result of the evenly number there. You can write any other number here like 3, 4, and 5. You can check it with yourself and just check the result that what kind of a result that the NumPy is given us. So that was our arrange command, and arrange command we can check that how we can evenly space our array. Okay, so after that we are now using our zeros and 1. Okay, so by using the 0 and 1 command, we can generate array with a specific column and a rows number. So if I want to if I want an array that contain the only one row, and it contain the number of zeros in it, only 0 number, no other values. So for that, I am using that command np.0, and if I want a one row and one column, so I have to put 1 here. So after running that command, you can check that it will show the result of that. Okay, so if I want one row and two column, and I want an array of 0 numbers, so for that the command is np dot zeros into 2, and it will give the result of this. So again, so these are the other example. Now we have a one row and a 5 columns, and for that we are using the npy dot zeros into 5. So notice that the numpy gives us the 0 dot. Actually, you can say that here a dot is also coming with the 0, so this indicates that these number are the floating numbers. Actually, there are two different numbers. One is the floating number. Floating number means that decimal is come with the number, and the other is the integers. Let me show that in integers what kind of results that we get. Okay, so these are all we have one row. Now if I want to make a array of matrix of 0, like I need a 5 cross 5 array, and I need a 0 in that array. We have just only one 0 number, so for that I'm using that command, which is numpy dot zeros 5 into 5. Okay, so the first 5 show the number of rows, and the other 5 shows here is the number of columns. And since we are using the 0 command, so it will give so it will give the result of this thing. Again, you can generate any format of a matrix just by changing the number of rows and the number of columns here, and it will generate that kind of result. Okay, so I tell you that if I want a number, I want a integer number. So for that, I have to command a d type is equal to integer inside it, and then now the dot will automatically remove from it and it will show only the integers number. So these are the numpy zero command that we can use as such. Now, if I want an array full of one, so for that I am using dot one command here. Like if I using the only uh, uh, one row and four columns, so I'm just using like this. And if I need a 3 at 7, like I have a 3 rows and 7 columns, and I need an array full of one, so I'm using dot one uh, command with the numpy. So these are the just basic, again, basic commands of the numpy. So the other command that here we have a line space. So actually, what are the line space? Actually, the line space is generating evenly spaced number or a specified interval. Like I have one array with the range of 0 to 20, and I want that there should be a number which come in an evenly spaced or specified interval. So for that, I have to mention that number here. So when you try to execute it, so it will give the result as like 0, 10, and 20, because I am giving the number 3. So it will equally specify number or the entire or the specific that entire number. Okay, so if I want to increase that number, let's suppose that I have arranged 0 to 20, and uh, I want that every other value should be evenly spaced. So I'm giving a number 20 and the result will come like this. So here these are the 20 number of values, and there will be the equal space between the 0 and this one, and this value to this value. So this is a line space command. So the next one is a I command that we are using in NumPy. Actually, the I command is used to create a identity matrix. Till now, we were working on array commands, that how we can modify array, and for that we use different multiple uh, commands. Okay, so now if I want to work on a identity matrix, so for that I am using a I command with the numpy. So for that numpy dot I 2. Okay, if you have any question, you can ask from me and I will answer you. Okay, so let focusing on from I command. Okay, so I command, as I told you, that is used to create a identity matrix. Now, if I want a identity matrix of 2 cross 2, so I'm just giving a 2 command here with the an I and using the npy command here. So it will give a result as such. Now, if I want a identity matrix of 4 cross 4, so I'm just changing the number into 4 and it will give the result as such. Now the identity matrix, we know that it has a 1 value on each of the diagonal. So again, if I want a 7 cross 7, so I just changing the number here, and the whole result will generate as such. So again, with this, if you want any an m cross n matrix of a identity matrix, you can use an I command, and in I command you just change the order and it will give you a result. Actually, because the identity matrix is very useful for many linear programming and algebra application. So whenever you use to work on the matrix, so you don't have to write this whole matrix inside your code. So you just write a command of I with your required m cross n order, and it will give you the whole matrix form. Okay, so the next command that I'm here to explain you is rand command. Actually, the rand command is that if I want array to create a random numbers inside it, so for that I have to use a rand command. Actually, it's create an array of a given shape and populate it with a random sample from a uniform distribution, which is between the 0 and 1. So for that, I'm using a random.rand command with the npy. So I want just just three random number inside my array. So I have to write just 8, and after just trying execute it, and it will give a result of this thing. Okay, so these three number are just the random numbers which come by using that command. Okay, if I need two random numbers in my array, so again I'm using the npy.random.rand into 2, and it will give us that result. Okay, so if I want in a matrix format like with 2 arrows and 3 columns, so you can just write it as such, and it will give just the random values in the array. This will give you a two random numbers with a uniform distribution between the 0 and 1. Actually, this is by default if you are using a random.rand command, so it will give you a values between the 0 and 1 because it work on a uniform distribution, and the range of the uniform distribution is from 0 to 1, as you can see check from the every results that is mentioned here. Okay, so the other command is the rand it command. Rand it command actually it randomize integers from the low to the high. Like I have a range like 0 to 100, and I want that this command should give me any random high number. So for that, I am using that command, which is np.random.randint from 0 to 100, and it will give me an 86. Now, if you try that command again, so it will give me some other random number. Okay, so I have that range, and I want that it should give me a 15 random number. So for that I have to write a 15 here, and it will give me a 15 random number inside this range. Okay, so if I want a result in a matrix form, so here I will give a format of a 3 rows and 5 columns, and it will give me a result of it. Okay, so the other command that we are using normally in array is reshape. Actually, by using reshape, we can give any shape to the array. Return an array containing the same data with the new shape. Suppose that we have an array uh, and it consists of 0 to 25 number. So for that, I'm using that arrange command, like I already told you about the arrange command and npy, and I'm sending that AAR just random name into it. And after running, it will give me that result. Now, this kind of array, I can also show you, I can also put in that shape. And for that, I am using that command arr dot shape. Okay, if anyone asks me a question, you can just open your mic and just randomly ask it. Okay, so I'll first try to complete the presentation, and after that you can just do it randomly by on your own, and then if you face any kind of a problem, then just ask me. Okay, so just return to the reshape command. As I told you that if I want to reshape that array into that one, like just with the one number 25 comma into that. So for that I'm using that arr dot shape. And if I want to convert this reshape command into the matrix form. So for that, I'm using the 5 into 5, which is the 5 rows and 5 columns. And for that, I use a reshape command, and it will show me that result of that. And after that, if I want to go back to that kind of that format, so for that, I'm using that simple AR, and it will give me the same result as such. Okay, so I think that we are moving toward our last command, which are the maximum, minimum, arc maximum, and arc minimum. Now I have some array and I have some random values inside it, and I want to check that what is the minimum value, what is the maximum value of the array. So for that, we are using the maximum and the minimum uh, command, and arc max and arc minimum is used to find the index location inside the array. Okay, so I have that array which have a number of range from 0 to 24. So now I want to know that what is the maximum value inside the array, and for that I'm using that maximum command as such with the array name. So it will give me automatically number of 24. So okay, so I want to know that what is the minimum array command. So for that I'm using dot minimum command, and it will give me 0 inside the array. Again, if I know uh, the location index of a maximum value, so for that I'm using the arc maximum, and it will give me a location here which is a 24. So on a location 24, the highest number is there in an array. And again, if I use I'm using the arc minimum to know the location of the minimum value inside the array, and for that I'm using that command, and it will give me a 0 location. It means that on a 0 location we have a minimum value inside the array, which is 0. So okay, so the final command that we are using in a NumPy is retype. Actually we are uh, just using different numbering format like integers and floating. Normally in an array we are working with the integers number, so we just want to know that what kind of a that type of the object that we are using in our array. So for that, if you want to know, just write that command ar.dtype, and it will give you that format that actually these numbers is coming from the integers 64. So in that workshop, so these are just the basic commands of the array that I showed you, and with that I also give you insight of how to use a Google Colab. What is Google Colab? Uh, s- so this is all the work uh, all about. Now we still have time. We still have 1 hour. So just open that uh, file and try to open the Google Colab and your machine. Try to run all the questions that I have mentioned inside the list, which I also read that try yourself out. Uh, mm, just uh, try to just execute all of the print statement inside it. So again, if you have any question and if you don't know about any step, you can ask me. And now just open your Google Colab and try to execute that Word file inside your Google Colab, and just check the result, that what kind of a result that you guys are getting. So that's all from my side, and still I'm waiting for your question if you need any help. while executing your Google Colab. So just ask me. So I will try to look your code and will try to work on it also. So that's all, and thank you from my side. Well, actually, I am still here. So if you have any questions, so then just ask. Okay, everyone. If there is no questions, then I'm finishing the lecture. And please kindly just practice on the Google Colab and the NumPy package and try to solve all the question that is mentioned in that Word documents that I think that Dr. Snape shared it with you all. And okay.